If you were lucky enough this summer to take some time off and go to the beach, how did you prepare to make sure that you had the best day possible? Depending on the high temperature, that would affect how many things you bring with you. In addition to a beach towel, how much water do you need to bring? What type of sunscreen and sunglasses will you need? Do you want a chair and an umbrella? What about snacks? And in my case, how much light reading do you need? Preparing for high-temperature gas chromatography is just like preparing to go to the beach because the first question we need to ask is, what is the maximum temperature we need to go up to? Typically, GC applications don't usually go above 350 degrees, and that's because most applications don't require it to go above 350. For those ones that do require heat above 350 degrees Celsius and some that need to go above 400 degrees, it is important to consider all of the supplies you are working with. Columns have a maximum temperature that is listed on their box, so that's easy to see. But other supplies, like septas and ferrules, also have maximum temperatures, and when operating above the norm, it is extremely important to select the supplies that can handle the heat. Also, what detector are you wanting to use? Some detectors, like FID, work great at high temperatures and are designed to handle up to 450 degrees Celsius. But other detectors, like mass specs, may end up having unintended problems when operating at temperatures above 350 degrees. High-temperature applications don't need to be a frustrating roll of the dice. They just need a little bit of preparation. And with a bit of preparing for high-temperature applications, we can perform successful high-temperature gas chromatography without breaking a sweat. Before we go into how to best plan for high-temperature applications, we need to determine if our application warrants the need of a high-temperature label. From semi-volatiles to flavors and fragrances to finished petroleum products, for the most part, these applications operate between a normal 40 degrees Celsius to 350 degrees Celsius, with occasionally requiring some sub-ambient starting temperatures. It's only applications like crude oils, polymer additives, and triglyceride that heat greater than 350 degrees is required in order to elute all compounds off the column. These are the applications that would be considered high temperature, and extra thought needs to be taken into consideration as to which high temperature supplies to use. But for all of these other applications, the vast majority of them that don't go above 350 degrees, specially designed high temperature columns aren't needed. And in fact, you would be better off selecting a more appropriate ultra-inert column for a majority of these applications. So if applications have a wide range of temperature limits, and you look at a column catalog, you'll find a plethora of maximum temperatures. How are these maximum temperatures defined? And what makes a DB5 different than a DB5HT? If you think about the parts inside of a capillary column, there are two main considerations: the stationary phase and the capillary tubing. When I say capillary tubing, I'm referring to the few silica and polyamide coated portion at the moment, but we'll break that down later. You may have seen temperature limits printed on column boxes and are aware that a wax phase has a maximum allowable operating temperature, often seen as MAOT, than a carboplot column. This is because this is the temperature limit for the stationary phase. This is the recommended maximum temperature of the stationary phase to ensure optimum bleed, stability, and inertness. There are other phases, such as PDMS, or a 5% phenyl that can be stable at much higher temperatures, but on their box states that either a maximum of 350 degrees Celsius for a regular column and 400 degrees for a high temperature fused silica column, and then up to 430 and sometimes 450 degrees Celsius for a deactivated stainless steel column. Why is that? That's because this is the temperature limit that is dependent on the type of tubing that is used. If there's one thing I want you to take away from this webinar, it's that the maximum temperature of the stationary phase is independent of the maximum temperature of the capillary tubing. And both of these are important to consider when selecting the right column for your applications. And it is extremely important to think about when you start to go above 350 degrees Celsius. Both the MAOT of the stationary phase and the capillary tubing are critical to your analysis. Go above the maximum temperature of the stationary phase, and your bleed can increase, or the K and retention index of your peaks can start to change. Go above the maximum temperature of the capillary tubing, and you can start to burn off the polyamide coating and cause the column to become brittle or even break. Sure, you might get lucky with the column and it might be fine by doing it just once, but you might not. And if you continue to go above the recommended maximum temperature, eventually something bad is going to happen. Much like a weightlifter who continually tries to lift a heavier barbell than they're ready for. They might not hurt themselves at first, or they could pull a muscle right away. Or after attempting multiple reps with too heavy of a weight, they end up not being able to lift their arms above their head the next day. The point is, the maximum temperature of the column matters, and it especially matters when you start to go above 350 degrees. So it's important to remember that it's not just about how hot you can go, it's about how hot you need to go, and determine the best supplies you need to perform your analysis successfully. Maintaining a leak-free system is important for all columns. Anytime you combine oxygen, column phase, and heat, bad things are going to happen. It's especially important when you are working at very high temperatures to start off with a leak-free system, in addition to making sure that your column is properly installed. Using gas clean filters are a great way to know if you have a leak before it gets to your GC, and helps protect your column from oxygen and moisture contaminants that may have crept into your gas line. On your gas filter, the blue indicator on top is the oxygen filter. Once this filter has reached 0.1 parts per million of oxygen, it will start to go from blue to dark gray. And when you see that nice blue filter turning gray, it would be a good indication that your filter is saturated and it's time to change it. The gas clean filter can be easily mounted onto the back of your GC system, and the new 8890 GC even has an option for our new smart sensor that, when connected to your GC, will even alert you when it's become saturated. One obvious sign that your column has a leak is an increase in the baseline. This column had become brittle and had a bit of tailing on the peaks, which would indicate some type of active sites on the front of the column. Normal protocol would be to clip about a meter or so from the front of the column and then reinstall it. But because this column had become brittle from being taken to temperatures above 350 degrees, tiny microfractures happened even with the most care taken in reinstalling this column. After reinstalling the column and looking at the bleed profile, the first injection doesn't look too bad. But as more oxygen is introduced into the column, and the longer it is held at 400 degrees Celsius, the more bleed we start to see. Eventually, the bleed is greater than 150 picoamps and would be very difficult to detect any compounds using this column. If you don't have any leaks and don't exceed the maximum temperature for the column, hopefully your column will last a long time. We work hard to make sure that both our column stationary phase and fused silica are robust enough to have a good lifetime at what we state is the maximum temperature for each column. But not everyone is as honest about the maximum temperature of the stationary phase and fused silica as we are. Some people say that their fused silica column can be taken up to 430 degrees, when we only state that the maximum temperature should be 400 degrees, which we say for a number of reasons. But let's focus on what happens to the stationary phase of a column and what happens when it is taken above where it should go and what it looks like when it starts to degrade. I'll give you a hint. Column bleed isn't the only thing you have to worry about when a stationary phase starts to degrade. Here we have two 5HT columns. Both are 30 meter 0.25.10 columns, which would be considered a standard high-resolution column for high-temperature applications. Both of these columns used special high-temperature fused silica, which I will talk about later, but we state that our maximum temperature is 400 degrees Celsius, and the other states that it can go up to 430 degrees Celsius. So which is true? Both look okay with one injection of test mix, but what happens over time, as both of these columns are taken to their maximum temperature for extended periods of time? Because I trust our R&D department, who determined the max of our DB5HT column, I compared what happened to both of these columns at our stated maximum temperature, 400 degrees Celsius. I injected a test mix, and then, after all compounds had eluted, I ramped up the temperature to 400 degrees Celsius, and then held it there for 1 hour. I repeated this test until both of these columns had operated at 400 degrees Celsius for a total of 120 hours. They both look okay initially, but let's see what happens. After a few hours of operating at 400 degrees Celsius, I started to notice that the brand X5HT column started to display an increase in the tailing factor of most of the compounds. Strangely enough, hydrocarbons started to tail, which don't usually get affected by active sites. And as this column was exposed to the adjuvant maximum stated temperature of 400 degrees Celsius, that peak tailing continued to increase, whereas the adjuvant J&W DB5HT continued to have good peak symmetry injection to injection. Peak symmetry is important in chromatography because poor symmetry would make it hard to identify if a peak really is a peak or if there is something wrong with the injection technique. But column efficiency is also important. So I looked at what happened to the theoretical plates per meter of tridecane over that 120 hours operating at 400 degrees when this test mix was duly injected onto both columns. At the adjuvant stated maximum temperature of 400 degrees Celsius, the brand X 5HT column started to degrade after 15 hours operating at 400 degrees Celsius. After 40 hours operating at 400 degrees, the efficiency of that column had dropped below 10% efficiency. And after operating at 400 degrees for over 100 hours, the brand X 5HT is even below 1% efficiency, whereas the adjuvant DB5HT is operating just as well after 120 hours operating at 400 degrees Celsius as it did on the initial injection. I know you're dying to ask, but what if they say their column can go up to 430 degrees Celsius? What happens? Well, we've already seen what happens at the adjuvant stated max. Here's what happens when these columns were taken to the brand X stated maximum temperature of 430 degrees Celsius. It degrades faster. Yes, there's a slight decrease in the efficiency of the DB5HT after operating at 5 hours at 430 degrees Celsius, which is 30 degrees above the stated MAOT, but it's not as dramatic as what is seen with the brand X5HT column. I saw this question come in through the chat, and I think it seems like the right time to speak to it. Yes, I repeated this test with multiple column sets and had the same results each time. So this is not a one-off. It's clear that when we state a maximum temperature, we have the data to prove that it has been made to last at that temperature. You can believe that when we state the max temperature of a high temperature column is 400 degrees Celsius, that it will last at 400 degrees Celsius, barring any unforeseen leaks or crazy matrices injected onto it. A sharp eye pointed out something from an earlier slide, that the peaks on the brand X5HT column seem to be shifting later as more heat was applied. You asked, why are the peaks shifting later? And this was something I thought about too. Normally, when you start applying heat, peaks will generally start to shift earlier as phase starts to bleed off of a column. This is a normal process as column bleed is a normal phenomenon. And that's what we start to see, or what we see with the adjuvant DB5HT column. Apply heat. Peaks start to shift a bit earlier, but that's to be expected with all columns and especially with high temperature columns. But that's not what we see with the brand X 5HT column. Right around 60 hours operating at 400 degrees Celsius, the K for the tridecane starts to increase dramatically. Remember, this was right around the time the efficiency dropped below 10%. And after operating at 400 degrees for 120 hours, the retention time for that tridecane has shifted from just under 10 minutes to 14 minutes. That's a big shift. So what's going on? What's happening inside the column? The best way I can think of to explain this is to think about the compounds going through the column like cars driving down a road. If a road is smooth, then your trip will take the time you expect. Your interaction with stoplights would be routine. Now, apply a temperature change, like a freeze-thaw cycle that happens every spring. Small cracks start to develop in the road, creating potholes that now you have to spend extra time avoiding on your drive. And the more potholes on your drive, the longer it will take for you to get to your destination. With the brand X 5HT column, that's exactly what's happening. As heat is being applied to the column, potholes where phase is being degraded are created. The more potholes that are created, the more untreated fused silica gets exposed. And untreated fused silica is extremely active and will cause activity for even the most robust of hydrocarbons, and will also cause a dramatic loss of efficiency. This is one of the reasons we always take the time to deactivate our fused silica before stationary phase is added to the column. By the time the brand X 5HT column has operated at 400 degrees Celsius for 40 hours, it already has enough potholes to really put a damper on your analysis. Whereas the Agilent DB5HT is still smooth enough to put into cruise control. So if it's the phase that starts to degrade, let's just add more of it to prematurely fill the potholes. Well, in addition to standard film columns not being a good idea for high temperature applications, which I'll get into later, the thicker film brand X 5HT column will still eventually degrade just like its thinner film cousins. It will just take longer. Whereas the Agilent column is still operating just as it did the first day it was installed. Now that we have established how a stationary phase can break down when taken to high temperatures, it's time to talk about the second part of the column that is just as important to consider when working at high temperatures, the tubing. There have been many types of GC tubing over the years, from bulky packed metal tubing that was very rigid to the first glass tubing that allowed for a more even internal surface but were extremely fragile to work with. Glass capillary columns offered a smoother surface and allowed for better polymer coating efficiency, but they were still rigid and had to be handled with care. It wasn't until HP that adapted the process for making fiber optic cables and the addition of a layer of silicone rubber, later polyamide, just after the glass capillary was drawn, made them flexible and much easier to work with. Today's wall-coated open tubular capillary columns have up to 6 layers of polyamic acid solution applied to the fused silica along the drawing path and are then dehydrated to form thin layers of polyamide on top of the glass, making them super easy to work with. But they do have temperature limits. Regular polyamide-coated fused silica columns have a temperature limit of 350 degrees Celsius. This is because that temperature, the polyamide will start to burn and flake off, exposing the delicate fused silica underneath. There is special high-temperature fused silica that is also available, but we recommend a maximum temperature of 400 degrees Celsius because even though there's more polyamide on the column, polyamide was only ever intended to go up to 400 degrees Celsius for brief periods of time and will eventually become brittle as well. It may take a long time, but eventually it will happen. This is why we recommend fused silica not be taken above 400 degrees Celsius even for our high temperature fused silica. For applications that need to go above 400 degrees Celsius, deactivated stainless steel tubing is needed. These aren't your grandpa's metal columns. The Agilent Ultimetal and ProSteel columns are both types of deactivated stainless steel tubing that we offer. And before they take a bath in stationary phase, they get a shower of silanes to provide a smoother and more inert surface before the polymer coating. These columns can operate at temperatures as high as 450 degrees Celsius and contain the same phases that are used in their fused silica counterparts, making them ideal for extremely high temperature applications. Has anyone seen this before? You're doing a bunch of high temperature runs, and a few days later open up your oven and are greeted with a completely clear column. You don't want to touch this column. This is the proverbial sleeping baby that could wake up and start screaming at the slightest noise, and one wrong bump or breath will cause it to fracture into a million pieces. This is what happens when you take a fused silica column above 400 degrees Celsius for a very long time. I said it before that polyamide will eventually burn off, and that's exactly what happened here. This is a column that was taken up to 430 degrees Celsius for 20 hours just to see what happened, because I like to push limits and see just how far I can push things before they start to break apart. This is yet another reason not to take fused silica columns above 400 degrees Celsius, even a high temperature fused silica column. But just like before, how I said some columns say their phase can last up to a certain temperature but can't, some fused silica can't even last at that maximum temperatures they set as well. This brand Y column is also a high temperature 5HT column, and the stated maximum temperature on the box was 400 degrees Celsius. But instead of the phase degrading, after 20 hours operating at 400 degrees Celsius, holes in the polyamide coating started to appear. This could be due to uneven coating, which could cause weak spots where the oxidation of the polyamide would start first. And then, after 5 more hours, 25 hours total at 400 degrees Celsius, the polyamide is no more. It's kind of crazy, right? This brand Y5HT column was supposedly rated up to 400 degrees Celsius, but magically made the polyamide disappear after 25 hours at its stated MAOT. Well, it didn't actually disappear. My GC oven was covered with flecks of dark polyamide, whereas the Agilent DB5HT column still looks great after 25 hours at 400 degrees Celsius and has all of its polyamide right where it belongs, on the column. I even used the Agilent column up to 120 hours at 400 degrees Celsius, and I only stopped then because the other column, the brand X column that I was comparing it to previously, broke. Both of these demonstrate that the Agilent high temperature phase and capillary tubing are more robust and a better fit for high temperature applications than both the brand X and brand Y high temperature columns. If you really need to do high resolution, high temperature gas chromatography above 400 degrees Celsius, then you would need to switch to a deactivated stainless steel tubing like Ultimetal. Our Ultimetal and ProSteel columns use the same stationary phases as the fused silica columns, but with the added advantage of the higher maximum temperature. Looking at these two chromatograms, can you tell which is which? You can't, because they have the same stationary phase and same film thickness, and they're made in the same locations. Sure, the fused silica will start off with the better efficiency, but as heat is applied and this column is taken up to 430 degrees, the fused silica column will start to lose its efficiency as the polyamide is burned off, whereas the Ultimetal column maintains its efficiency throughout its extended usage at extremely high temperatures, and the chromatography looks pretty great to me. Now that we are all agreed that when you need to go above 400 degrees Celsius, the best thing to do is to switch to a deactivated stainless steel column, next we need to go over how to choose the best column for your application. With gas chromatography, people think sometimes that the best option to get heavy compounds off of a column would be to just keep applying heat. Sure, You can add heat, and depending on how heavy the compound is, if it makes its way onto the column, it will eventually come off. But that could take a very long time and a really high final temperature. There are other things that we can do to help our compounds get off the column that have nothing to do with temperature. For instance, if you look at the method translator tool, a few parameters will pop out at you. We can increase our column flow, decrease the length of our column, pick a column with a thinner film thickness, or a column with a larger internal diameter. If we need to analyze heavier compounds, then we should first employ a combination of all of these components before turning up the final temperature. And if you don't need to look at these heavy compounds and are only turning up the heat to burn off the gunk, then you may want to look into using backflush with your analysis, which my colleague and I talked about in an earlier webinar titled How to Keep Your GC and GCMS System Performing Like New. Without increasing heat or changing the diameter of our column, let's take a look how film thickness and column length have an effect on an isothermal run with test mix compounds. As you can see, by decreasing our film thickness from 0.25 micrometers to 0.1 micrometers, we would be able to decrease our runtime from 23 minutes to 12 minutes. And if we want to easily decrease our runtime even more, if we cut the column in half, we can even decrease the flow from 1.7 mils per minute to 1 mil per minute and still elute all of our compounds in less than 8 minutes. We've been able to decrease this runtime from 23 minutes down to 8 minutes, all without making one change to the temperature. I know that these are pretty light compounds, but I use them as an example of how we can easily see that short, thin film columns are what you need when you want to get compounds out faster. Now, for really heavy compounds like simulated distillation, we will need to go shorter, increase our diameter, and go up to temperatures greater than 400 degrees Celsius. So that means we need a short, thin film deactivated stainless steel column. Here come the groans. Metal columns have gotten a bad reputation for being difficult to install, but I assure you that the Agilent Pro Steel and Ultimetal columns are not the columns of the past. Sure, when trying to cut some glass-infused metal columns, you will have to use more force to barely get a score on the column. Then, bending it to snap the column can require a lot of effort, and even when it does break apart, some manufacturers require a second tool to file the tip of the column to remove any jagged edges. Those metal shavings could end up inside the column and create active sites, which would be bad news for your chromatography. Plus, since this material is so thick, it's really difficult to install in your multi-mode inlet. I know when I installed this glass-infused metal column, it reminded me of when I tried to put on skinny jeans after being on holiday for 2 weeks. I mean, I could get them on, but it wasn't the most comfortable experience. And when it comes to multi-mode inlets, it's very important to make sure that the column length above the ferrule is about 12 to 13 millimeters to ensure proper peak shape. And with a thick column like this, it would be very difficult to make sure that the tip of the column is where it should be. Whereas with the Agilent DB-HT SimDisc Pro Steel column, all you need is one tool, the ceramic cutting tool that I'm sure you have floating all over your lab to easily cut your column. You only need a bit more pressure than with a fused silica column of that same diameter, and it will easily snap when it's bent without much force. And you will end up with a nice clean cut. And a clean cut means better chromatography, as you can see in this test mix. All of our peaks are nice and sharp, letting us know that this column is ready to use. Let's take a look at how these two columns compare with a heavy hydrocarbon sample like Polywax 655. For those of you who haven't worked with Polywax standards, they are waxy pellets that are made up of a wide range of alkanes. In both GC columns, all hydrocarbons are detected, but the brand X metal SimDisc column has a significantly higher column bleed than the DB-HT SimDisc. The increase in column bleed that is seen in the brand X metal SIMDIS column begins as the oven is increasing above 400 degrees Celsius and continues up to a final column bleed of 87 picoamps at 430 degrees Celsius. This would make integrating and detecting later eluting hydrocarbons much more difficult. By contrast, the DBHT SIMDIS GC column only has a bleed of 17.3 picoamps at 430 degrees. And if we zoom in on this portion here, we can see a nice, clean baseline separation. And if you're curious about the resolution between C50 and C52, it's 3.36, which indicates more than a baseline separation and makes a clean integration super easy. What about even heavier samples? Here are 3 injections overlaid of Polywax 500, 655, and 1000. With the remarkably low bleed for the DBHT SIMDIS column, we can clearly see the alkanes ranging from C12 up to C114 and even C116 without the need for background subtraction. Anyone who has worked with alkanes greater than C100 knows how tricky they can be to prepare and analyze. In addition to choosing the right solvents, it's also important to heat the standard to get all of those heavy alkanes into the liquid phase. And even when you transfer your hot sample to the vial, they can cool down pretty quickly. And even though they are still injected onto the column, they can increase the baseline as all of those unseen hydrocarbons keep on flowing through the column. It can take even more heat, like needing to go up to 450 degrees Celsius to really push those heavy suckers off the column. This brings up an excellent point about just because you don't see any more peaks in your chromatogram, it doesn't necessarily mean that your system is clean and ready to go. It's possible that you still have some heavy compounds hanging out, slowly making their way through the column, or they could be stuck in your liner. And just as much as your column flow, column dimensions, and final oven temperature, the supplies you use are just as important to your high temperature analysis. For GC applications, there are so many supplies that you can pick from, and people inevitably end up having a favorite septa or liners that they like to use. But these supplies have temperature limits of their own, and when performing high temperature gas chromatography, it's very important to choose the ones that can stand the heat. Luckily, we have many different options. For septa, I would recommend our BTO, also known as bleed and temperature optimized septa, that are plasma coated and can operate up to 400 degrees Celsius for long periods of time and even a bit higher for brief periods of time. When it comes to ferrule selection, there are 2 options: graphite ferrules and multi-metal flexible metal ferrules. Both of these have a maximum temperature limit of up to 450 degrees Celsius. I know that people like the polyamide graphite ferrules, also known as Vespite graphite ferrules, because you can use the self-tightening nuts with them. But those ferrules have a maximum temperature of 350 degrees because, as we've talked about previously, polyamide will start to burn off when it is taken above 350 degrees. And when the coating on the ferrules start to flake, it will start to leak, and leaks kill columns. So please use regular graphite ferrules with standard nuts or multi-metal flexible ferrules with our CFT capillary flow technology nuts for high temperature applications. For liner selection, which is very important for high temperature applications, and we'll get more into that in just a minute, know that standard liners will be just fine for your analysis. If you're going hot, it's less likely that you are analyzing difficult compounds activity-wise. More than likely, high temperature analysis are looking at hydrocarbons, and you can use yes, you could use the ultra-inert liners, but you are not going to see as much of a benefit as you would in a standard GCMS application. More importantly, for liners and sample introduction is to think about how to best vaporize your sample and get all of those heavy compounds onto the column. When it comes to getting the best vaporization for heavy compounds, the inlet that does the best job is the multi-mode inlet, also known as MMI, or program temperature vaporizing inlet, also known as PTV. Both of these inlets have the capabilities to ramp the temperature of the inlet once the sample is injected. This can allow for a larger injection volume because when you start out with a lower temperature, there is less solvent expansion, and this also helps to decrease sample backflash issues. Backflash is when the solvent expands past the capacity of the liner and goes the only place it can, toward the septum. Also, with the ability to ramp the temperature of the inlet independent of the oven, the MMI can limit the thermal exposure for thermal liable compounds, which will make their way onto the column first, and then, as the temperature of the inlet is increased, the heavier compounds will also vaporize and make their way onto the column as well, which will help to limit the thermal discrimination and improve recovery for the heavy compounds. To aid even more in sample vaporization, liner selection is important. Since MMI and PTV inlets don't have gold seals and can be hard to clean, it is very important to stop the non-volatile crud before it gets onto your column or dirtying up your inlet. Liners with glass wool or dimples are some of the best you can use to stop the crud and protect your system. And dimpled liners even offer more surface area to aid in vaporization and further help to decrease thermal discrimination. And when the proper liner and inlet are used together, we can decrease our detection limits and achieve better accuracy of our data. We've talked about which columns and supplies work best for high temperature applications and why, but the last thing we need to talk about is which detectors should and should not be used for high temperature applications. There are many things to consider when selecting the right detector for your application, mainly being the type of compound you are looking at and which detector will provide the best sensitivity. Flame ionization detectors are super sensitive for detecting hydrocarbons and are capable of detecting quantities as low as 10 to the negative 13 grams per second, which would be like the ability to detect the DNA in one cell of a hummingbird every second. Plus, the FID can handle very hot temperatures. It could probably even handle temperatures greater than 450 degrees Celsius, which is why FID is recommended for high temperature applications. Because detectors have temperature limits too. And trying to use a detector above its intended max would be like trying to drive a car at 50 miles per hour in first gear. Sure, you can do it, but eventually you're going to burn out your clutch. For some reason, lately, I've been getting a lot of questions about using mass spec for high temperature analysis, and I always ask the same questions back. What compounds are you looking at? How hot do you need to go? And are you sure you don't want to use an FID for that? Sure, the GC oven can go up to 450 degrees Celsius, but your mass spec has limits. Also, your mass spec is great for detecting a wide range of compounds, and with that increase in sensitivity also comes the potential of an increase in background noise if you inject some really heavy samples, thus canceling out the detection capabilities of the mass spec. Not to mention what can go wrong based only on the temperature limits of the consumables used with the mass spec. For instance, the MSD transfer line, whether you are using a self-tightening nut or a standard brass mass spec nut, for that polyamide graphite ferrules are used. And as we've discussed before, these ferrules have a maximum temperature limit of 350 degrees Celsius. When taken above 350 degrees, they will also start to shrink after thermal cycling, and the polyamide will start to burn off, both of which will cause leaks in your mass spec. Normally, we would say to use a graphite ferrule for temperatures above 350 degrees Celsius, but this is a very bad idea with the mass spec. Graphite is softer and can compress, and when you add the vacuum of a mass spec, can potentially end up getting sucked into your source and gunking it up, or into the turbopump, and then you have a real problem. But say you use a polyamide graphite ferrule, also known as a VG ferrule, and go above 350 degrees. What happens to the source? The newer ion sources are capable of going up to 350 degrees, But if you have a leak in your system, your filament is going to burn out faster, forcing you to have more downtime to vent your source and replace your filaments. And what about after your source? Generally, you aren't going to take your quads above 150 degrees, and going from 350 degrees to 150 degrees is a huge temperature drop. That would have me worried about compounds recondensing in my quads. So before you try to do a high temperature application on a mass spec, ask yourself, do you really need mass spec? Are you aware of the risks about going above 350 degrees? Also, if you're only trying to go hot to bake out your column, have you considered using backflush? And if your analysis does require mass spec, but you are analyzing difficult compounds and want to use a low bleed column, have you thought about using an MSUI rated column? Here's what can happen when you use a non-MSUI column on a difficult sample that requires mass spec and it's taken above 350 degrees Celsius. This is a brand X5HT column where I analyzed one of our new 8270 standards at a concentration of 5 microgram per mil over 45 hours operating at 400 degrees Celsius. These environmental samples can be gunky, which is why people want to try and bake out the crud and go above 350 degrees Celsius. But with the brand X5HT, you won't just lose sensitivity. Like we saw before, the inertness will begin to suffer as the phase starts to degrade. So not only will we not be able to detect some compounds, but our peak shape will suffer, and then our QC won't pass, and then maintenance and downtime will be needed to try and get those compounds back. Whereas the DB5MS ultra-inert column and other MSUI columns have been designed not only to have low bleed and help enhance sensitivity of the mass spec, they are also ultra-inert and ideal for difficult compounds. As you can see, while the DB5HT does look pretty good, the DB5MS UI column looks even better for difficult compounds like trimethylphosphate. And then when we compare to the same test mix analyzed on the brand X5HT column after it had been operating at 400 degrees Celsius for 45 hours, we see significant tailing for almost all of the compounds, and propionic acid is almost undistinguishable. We've already seen how the Agilent 5HT stationary phase has superior performance and lifetime in comparison with the brand X 5HT stationary phase. But if you're analyzing difficult compounds on a mass spec, you want to make sure you start off right with an MS Ultra Inert column for the best results, and keep your mass spec under 350 degrees. In summary, you always want to make sure that you are selecting the right column for your application. And when it comes to high temperature applications, Agilent J&W high temperature phase on our high temperature fused silica are stable for extended periods of time, up to 400 degrees Celsius. Yes, our high temperature fused silica columns have great lifetime at 400 degrees. But if you're going to go hotter, like up to 430 or 450 degrees Celsius, then it is time to switch to a deactivated stainless steel column like our Ultimetal or ProSteel GC columns. They use the same stable phases, but if you're going to operate at temperatures above 400 degrees, you need robust tubing that can handle the heat. And unlike other metal columns, Agilent ProSteel and Ultimetal columns are easy to cut and only require one tool to make a clean cut, making it easier to use, and ensuring a better connection at your inlet and detector. And speaking of connections, your consumables are also important in high temperature applications. Use consumables that can take the heat, like BTO septa and graphite or Ultimetal flexible ferrules, to ensure that you have a leak-free connection. And select the right liner for your application. It doesn't have to be one of the ultra-inert liners, but it does need to help fight against thermal discrimination. And lastly, we do not recommend mass spec to be used for high temperature applications for many of the reasons we've spoken about today. There's no truth to a column labeled high temp will have a longer life than a mass spec column, or that just because someone says that their column has a higher maximum temperature means that it's better than another one. I think we've shown that the stated maximum temperatures are not always what they appear to be. And at Agilent, when we state a maximum temperature for a column, we stand by it because we have tested it not just for stationary phase, but for the capillary tubing as well to ensure robustness and efficiency at that maximum temperature for the column lifetime. But if you do need to use a mass spec for your analysis and aren't going above 350 degrees Celsius, a better choice would be to use an Agilent mass spec ultra-inert column. They've already been designed to have low bleed and a superior inertness for difficult compounds.